So what I want you to first imagine is that when something goes to fall through the air, generally it doesn't move in one dimension. It moves in two. You drop something, kick something, knock something off the table, hit a ball, punch somebody. I mean, they're going to move in two dimensions. What a lot of people don't recognize is that the motion is separate. There's the up and down part of the motion, and there's the left and right part of the motion. When the object leaves the table, it no longer has the support from the table. I know it's a ridiculous statement, but it's not like cartoon characters, which fall down once they realize they're no longer on the table. The moment it's not on the table, gravity starts pulling it down immediately. Doesn't change the fact that it's moving sideways. What I mean by that is, the moment the ball is here, it still has the horizontal velocity it had a moment ago. We're going to call that Vx because it's sideways. But suddenly, it's experiencing a downwards acceleration due to gravity. So in this particular example, the object doesn't have a downwards velocity to begin with. It had a sideways velocity. But suddenly, this acceleration is going to begin to accelerate it downwards. The most important thing I say here today is the next sentence. The downwards acceleration doesn't change its sideways motion. The downward acceleration doesn't change its sideways motion. So right now in your notes, the implication is that it's going to hit the ground, still moving sideways at the same speed it left the table. The sideways motion stays the same the whole time. Its up and down motion changes. So in this case, its vertical motion will accelerate, but its sideways motion will not. So after a few moments in the air, the object's going to be, say, right here. It still has a sideways velocity. This has not changed. It will always be the same value. But now, because it's been accelerating downwards a little bit, it also has a little bit of a y velocity. Now, what that really means is that it's moving this way. It's moving at an angle. But we have two separate components of motion. You see why we did the trig today and why the trig is important. Now, one of these is going to be changing the whole time, and one of these stays the same. After a few more moments, the ball's going to be like right here. It's still going to have the same sideways velocity that it's had the whole time. But now, because it's been accelerating downwards for a little while longer, its y velocity is becoming a larger part of its motion. In fact, by the time it reaches the ground, its y velocity will probably have grown to be greater than its x velocity. This is what a projectile does. A projectile moves in two dimensions, but accelerates in only one dimension. So what I suggest we do is, when faced with a projectile, we immediately divide up our problem and create a vertical side. I spelled vertical wrong. A vertical side, yeah, and a horizontal side. The vertical side will always have these things. And I'm going to just switch stuff so that there's y's in here. Just putting y's in there to force me to think that this is the up and down part. So not delta x, but delta y. Not v initial y. Not v final y. Acceleration in time. This side, There's only three things. Because there's no acceleration, how far it goes only depends on how fast it's going. The speed doesn't change, so it's only those things. Here's the crux. Those two have to be the same. It moves sideways for the same amount of time it moves up and down. All projectiles, that's the thing. You solve for time on one side and you use it on the other side. This is our mantra. This is what we'll use for all projectiles. It's a simple way to organize ourselves. The hard part is that right now you have this written down, but you have no instructions as to what those things are. So I'm going to give you a ton of numbers, and you have to try and spit them at this thing and figure out where they go. So take a few seconds, just a few, and annotate your chart here. Just tell yourself the things that you need to know. Like, this is how far it falls. An object falls 2 meters off a table. Or an object falls from a table that's 2 meters high. It's a tall table. But tell yourself what that number is going to be. Because the problem is going to have a lot of numbers in it. Think about all the things the problem is going to have to tell you. This is how fast it was moving up and down at the start of the problem. Was the ball thrown upwards, kicked at an angle? It's how fast the object was moving up and down. You're never going to be given this one. That's how fast it's going when it hits the ground. Very seldom does that something a problem gives you. We don't know how fast the football landed. We know how fast the football was thrown. You follow what I'm saying? So yes, if I want to create a problem just to screw you over, I would tell you how fast the football landed, but that's not how the world works. I want to know how fast the ball left the bat. I don't really care how fast it was traveling when the guy caught it. Right? You see how the world kind of is like that? This is going to be gravity. Every time. Right? It's gravity. These are projectiles. We're not going to be talking about an object thrown in space. It's not a projectile anymore. Yes, they could screw you over and put it on the moon or put it on Mars. But that just changes what that number is. It's still going to be the acceleration of gravity. For all intents and purposes, in the next 3 days, it's 10. Right? We're going to do this on the Earth. I don't need to make it harder just to be interesting and show how smart I am. That's not the goal here. The goal is for us to recognize that the connection, time, almost every one of these, you're going to be figuring out how long it takes to reach the ground. Keep that in mind. I'm probably going to try and give you those 3 pieces of information somehow, so you can figure out how long it's in the air. This, I think, is obvious. It's how fast it's moving sideways. The most common mistake is to put that number somewhere in the vertical. Because it's in meters per second, people put it here every time. But I'm hardly ever going to give you that number. So focus on, likely, if it's moving at the start of the problem, it's probably the horizontal speed. It's very, very likely. A plane is flying and it drops something. It was flying horizontally. The plane was probably not flying down. That's very unlikely, right? So you got to kind of reason those things out. This has a name. It's often called the range of your projectile. It's a horizontal displacement. How far away from the edge of the table it lands. How far away from the tee does the ball land? Something like that. But we often call that the range. All right, so we have time to do one. And I'm going to make it super simple. You roll a Hot Wheel car off your table. You want to find out where it lands. These tables are 86 centimeters tall. So you roll a Hot Wheel car at 0.5 meter per second off an 86 centimeter table. Where does it fall? Now, just to do this with us together, I'm going to put all that information right here. But understand, put this in your notes like as an aside. Stuff doesn't take very long to fall. In real life, if you calculate the time it takes something to fall and you get like 10 seconds, no. It's a 0.5 second for something to fall anywhere in this room. So off the tables, You might be able to get a full second from the ceiling. But everything in this room, when something falls, it's half a second or a little bit more. So when you do this calculation, if you get like 4 seconds, that should be a big warning. Check your work. Stuff doesn't take long to fall. So V, Y, V final Y, A, T, and delta X, Vx, and T. I said that the table was 86 centimeters high. That's code for it's 0.86 meters. I will have to expect you to know the difference between centimeters and meters. Put your stuff in meters. And this object's traveling sideways at 0.5 meter per second. And I would like to know where it falls. So I'm going to put the stuff that I know into my chart. Like, so I don't screw it up, the sideways velocity. Get it over there. Get it out of the way, because it's not going to tell you very much here. It falls downwards. Up and down is going to be a problem for these. Because you got up and down, and you got left and right. So you're going to notice that when I start thinking about it, I'm probably going to put a little thing here and put plus, plus. So I can take control over what has to be made positive and what has to be made negative. Because it fell downwards 0.86 meters. And you're going to slap yourself the first time you don't do that right. Luckily, the problem will warn you because you'll have to take the square root of a negative number if you screw this up, so you'll know. This is one I think that's easy. It's downwards at 10 meters per second squared. Very likely to be gravity every time we do these. The one you won't think about is the fact that it rolled off the table and had 0 initial velocity. You're going to put the 0.5 here, I promise. So tell yourself right now not to do that. Just because you're given a velocity doesn't mean it has to be the starting velocity. It is a starting velocity, sure, but not the up and down one. Notice you got 3 things. Right? 3 things on that vertical side. That's all it takes to figure out the time. Grab that calculator, fire it up. This one's straightforward. Yeah, you're going to need one of those. And like I said, it's almost always going to be this top one. And with a 0 for the initial velocity, it's an easy one. So I'm going to have negative 0.86 equals 1/2 times negative 10 t squared. You need t. And I promise it's not going to be very long. We get a half second, like 0.4 something. I know. 0.86 divided by 5. Take the square root. Yeah, 0.416. 0.416?
0.172.
All right, so I'm going to say 0.42. How's that? About half second. Yeah. Notice, I don't write it in one place, I write it in both. The time is the same for both. So when you find the time, it goes in both places. How are we doing? Not terrible? So, where does it land? It was traveling at 0.5 meters every second sideways, and it fell for 0.42 seconds. So, about 0.2 meters. Maybe 0.21 meters. 4 times 5 is 20, so I'm thinking, yeah. So 20 cents, it fell this far away from the table. Okay, I believe that. Now, you do understand, this is like basic. Obviously, where we're going to go is on one of those, right? That's all the trig stuff. That's why we got to start. We'll start basic. But by the end of the day tomorrow, I want to be doing something like those. We're going to do nothing but practices for the next 2 days. I think by Friday, we'll be done practicing this. Friday, we're going to actually throw some stuff around the room and have some fun.